Hey, great. First of all, I'd like to thank the organizers for this wonderful conference and the Isaac Newton Institute for their hospitality. It's been a real boost for me. I've been out of doing Regge calculus proper for a little while, been doing applications of it, but it's animated me to get back in and engage with the finite element community a little bit more invasively. So thank you for the invitation. I will talk about general relativity one block at a time, and I have the philosophy for the talk here, but I put Tullio Regge's abstract up there so you can read it on your own. I'm not going to go through and read the slides. But that's Tullio Regge, affectionately known as the Feynman of Italy. Picture receiving the Dirac medal to the left, and then I asked him how he came up with Regge calculus when I was a graduate student, and he told me that in Turin, depending on how you lean, he went to a barber shop and they had the skewed mirrors, which I'm showing here, which shows the curvature. And he thought, what a wonderful way to represent the curvature of space and time, which is the essence of Einstein's theory of general relativity. So that's sort of direct from him. Whether it was like a fish story and embellished in time, I don't know, but that's what he mentioned. So the philosophy and motivations for what I'm going to be talking about today. I do not know whether Regge calculus will be a viable numerical tool for this community. I don't know whether it's going to help you with your extreme mass black hole inspiraling problem. Probably not. But I think it has a lot to offer this community. So Alexandrov, A.D. Alexandrov, was a foundation for a lot of the geometry of polyhedra. And his student Pogolarov, who studied geometry in the large, and his advisor, Alexandrov's advisor, Delaunay, and Delaunay's advisor, essentially his advisor was Voronoi. And all these concepts will be here. But the foundation of what Tullio Regge did was to take a lot of this foundational work, Russian mathematics, and apply it to the field of general relativity. And had wonderful foundations to work on. What I'm going to emphasize today are 2 points. And I want to give you an introduction to Regge calculus, but I'm going to emphasize 2 things that, as was emphasized by Lee, that this is a great platform to look at geometry, problems of geometry in the large, very difficult problems. We can look at complicated topologies, and it's rather at home in that environment. One does not have to worry about the things you would have to worry about doing Ricci calculus as opposed to Regge calculus. So, and it's general relativity without coordinates, which is a diversion from what we heard earlier with Lee. But again, I don't know computationally which will be more viable, and it's interesting to look at. But one thing I have observed in working in Regge calculus for a few decades is that the laws of gravitation that you're familiar with in this room here, that we study in textbooks, appear to be encoded locally on the lattice in a far simpler way than in the continuum. And you average out over blocks to recover the continuum version. And I'll explain that in a talk here. So when we're looking at Regge calculus, it's a very different mindset. And for the mathematicians and the GR people, very different mindset. Whereas the finite difference people will take the continuum theory and discretize it, the Regge calculus people will take the principles of relativity, equivalence principle, flat interior blocks, and build from the principles of general relativity the equations from the geometry itself. So it's the opposite way of doing it. That gives you a lot of deep insight. That's the kind of thing that Alexandrov was alluding to that may give you rise to doing things differently in the continuum than you would ordinarily do in a discrete setting. I hope that's clear. And I'm going to have a conjecture. And my conjecture, I have to, Anil, I saw his paper after working in Regge calculus for a long, long time. And I picked up some of his dissertation and work in the field. And I thought I had an epiphany in life. It was just fantastic. So I have a conjecture, which I think the mathematicians will like to hear, if it's true, that Regge calculus is just discrete exterior calculus applied to general relativity. So that's the conjecture I have. So no need to learn everything I'm talking to you about, except don't go away. I may be wrong, but I think there's some interesting things that go on. So I stole pictures from Schultz. So I have 3 parts to the talk. So I'm going to go over now what Doug had wanted me just to go over a little bit of the foundations of Regge calculus and general relativity. Some amazing features I see in Regge calculus, which was why I thought it was simpler, and numerical applications. I'll go over, discuss the numerical approaches. So Einstein's theory we heard throughout many of the talks here, that the curvature of space-time is how Einstein modeled the gravitational field. So it's a pseudo-Riemannian geometry, and the essence of his equation, which is G is equal to T, is that the curvature of space-time, the G, acts on matter, telling it how to move on the black holes, and so forth, and the gravitation, you know. So, the matter, neutron stars or whatever, black holes, not black holes, neutron stars, react back on space, telling it how to curve, and it's a coupled system in that way. So that's the essence of GR. So we need to get at the curvature, a measure of curvature, and build the Einstein tensor. So as I said before, Regge calculus, I'll do this from scratch. But you saw that in previous talks, you start with G, you take a derivative, and you get connection coefficients. You take a derivative, you get the Riemann tensor. And from the Riemann tensor, you can create the Ricci tensor tracing out, and you can create the scalar curvature, and then hence the Einstein tensor. So this is real. We see this in images from our cameras. This is a Hubble Space Telescope image of lensing in the cosmos. So there's an intervening galaxy there that's causing the light from a quasar to go 2 different routes into the telescope. So you're seeing multiple images of the same quasar or galaxy, and you also see them distorted with these rings around there. So this is the curvature of space-time telling the light how to bend. So what I'm doing in Regge calculus in this beginning of the talk here is to take this equation here and show you how this equation, which doesn't look very nice compared to that one up there, but I'm not Einstein and neither was Regge. So, but this is beautiful to me. If you work long enough with anything that's your own theory, it looks beautiful. And then the metric is the edge length. We're going to bypass the connection coefficient completely. No junction conditions of the normals, the tangent vectors across the boundary simplices. And we'll just talk about the edge lengths again. You can model complex topologies. It's at home in triangulating 4-dimensional, well, as Lee said, maybe not all of them, but you can triangulate very complicated space-like hypersurfaces and start looking at topological issues. But the very foundation of Regge calculus is that the space-time is built from simplices, 4-dimensional triangles. And they're glued together to form a lattice so that they only intersect on their boundaries. The triangle faces in 3 dimensions, or the tetrahedral faces in 4 dimensions. So this is a space-time block. We'll assume that the geometry inside of the simplex, the central object here, is a flat Minkowski geometry, signature minus plus plus plus, for those of you that love that. And then the boundary, I show here the 5 tetrahedral boundaries around the simplex. This is the bounding tetrahedra for the simplex. Now, why is this important to use a simplex or use in more general settings rigid blocks? Because it can be a little more general than this in some cases. And the reason is because if I specify the edges, then the entire geometry of that simplex is defined. So if I specify all the edges of the simplices in a lattice of space-time lattice, then the geometry is well defined, and we can start calculating. And then we act like our home in the universe is not a continuum, but we live on this discrete simplicial manifold, and we call up Einstein and says, you know, your principles of GR, how do I apply it here? So he says, well, just parallel transport some gyroscopes around here and there and start building things. So, so this is what Tullio did, and he gave a very beautiful expression for the action, the Hilbert action in Regge calculus. So this is when Einstein came up with his equation, Hilbert almost simultaneously came up with the Hilbert action principle that gave his equations when varied this action with respect to the metric geometry. And the Regge-Hilbert action will give the Regge equations when you vary this with respect to the edge lengths. And this is just we heard these, the defect angle, I'll define these in areas. So curvature, how do we get at curvature? Well, let's take a model of the Earth so I can give you in the right mindset. If we start out at the equator, and I have a vector, and I'm going to go, it's too hot down there like it is in Florida, so we go up to the north, and it's a little warmer there than we think now. But I carry the vector because it's uncharted territory, parallel to me the entire journey without wavering the gyroscope. I get up there, no more polar bears that I came across, so I feel confident, but it's too cold nevertheless for me, so I want to go back down to the equator, so I take a right-hand turn. Not necessary to turn the spear because it's not dangerous on the journey up, and I go down from the pole down to the equator again. Now I'm on the equator, and I have some people that don't like me so well, so I take another right-hand turn so the spear is behind me so they can't come up from behind. Never turning the spear the entire journey. Go back to the beginning, the spear changed by 90 degrees. And my friend says, why did you rotate your spear? And I said, I did not. And then yes, it must be curvature. So curvature measures the angle the vector rotates divided by the area circumnavigated. In this case, pi over 2 and 1/8 the quadrant of the Earth. And that gives you the standard Gaussian curvature. And curvature in general relativity is encoded in the Riemann tensor, which we'll start building. And that is a bivector valued 2 form. It's essentially a machine which you plug in an area, and it gives you out a bivector of rotation on the left. So let's go work up from 2 to 3 to 4 dimensions, just so we can see things clearly. So in 2 dimensions, I have some triangulated toroidal type geometry, and I look at a very an area region of that, one vertex, in this case with 5 triangles hinging on that vertex. And this is what it looks like under the magnifying glass. Now, you know, when you have something like this, it is ordinarily puffed up a little bit. So what I'm going to do is I'm going to take this thing and I'm going to press on it, and it will split. And this is the deficit angle here that we talk about in Regge calculus. It's 2 pi minus the sum of the internal angles. So here it is, pushed down, just as I did with this model here. And I'll just pass that around. You can, well, now I'll take it one. I have one more prop. So, and then, so this is the deficit angle, and curvature is angle the vector rotates, which is in case this angle here. If I bring a vector around, which would be 2 pi. Oops, sorry. It's great. Da, 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 da. Transitions are not good. So it's 2 pi minus the sum of these internal angles. Now, that's the same as I get if I take a vector and parallel transport it around that curvature singularity, the codimension 2 object. It's 2 dimensions, 2 minus 2 is 1. It's the vertex where the curvature is concentrated. It's canonical. And you hear in Regge calculus, everyone worries about curvature singularities, conical singularities. Well, we'll see how to handle those in Regge calculus. But you have to divide by an area. So I'm going to make a ansatz that I'm going to say that Regge calculus uses Voronoi lattices for the area and its definition. If you do not use that, you will not get canonical Regge calculus. So those of you that are using different dual lattices, it does not work. Regge calculus will be a different theory. That discrete geometry will be a different theory with properties that are not so nice. In other words, you'll not have 1 equation per edge length. You'll have ordinarily more equations per edge length to deal with. So this is a big difference. So the curvature then is the deficit angle divided by the area circumnavigated. So this is a codimension 2 hinge, and that's the dual. So dual to a vertex would be this Voronoi area. And that's for the object that I have, that's essentially this area that fits over onto this best laid plans. So this is the block which I'm showing, and this is the area, and you just add up these kite areas to get it. So we have to get at these kite areas, and if you look in the discrete exterior calculus, you see these, and I was like, oh, fantastic! I am making a connection with something that's broader and deeper than what I've been working on for just in GR. And we've seen the results of Cheeger, Muller, and Schrader. So if I just take this in a naive way and take an icosahedron and subdivide it, project it out on the sphere, use geodesic edge lengths, and analyze the curvature this way with the Voronoi areas, I get a curvature which is very closely to 1 over r squared for this, as I should. And it's not perfect. And I look at the convergence in a number of subdivisions, and I get a convergence, in this case, with a slope of 1.4. So it's just under second order convergence for this simple model that I did. In 3 dimensions, now the building blocks are not the 2-dimensional triangles, they're tetrahedra. So we have the tetrahedra here, and these tetrahedra will pack together. In fact, this one is an isosceles tetrahedra. So it will pack into a nice lattice, a self-packing cell. And in my general relativity code, when I'm doing the black hole binary and spiral with waves, and I take my magnifying glass and look at a local region, if I do the lapse and shift correctly in Regge calculus, then the tetrahedra should look very close to the isosceles tetrahedra. In fact, I think if I pack these in this room around here, I have to stretch the last tetrahedra to make up for 10 to the minus 20 radians because of the Schwarzschild curvature in this room here. So there's a little deficit angle in this room. But we use tetrahedra. And tetrahedra there'll be numerous tetrahedra that share a given codimension 2 or edge. 3 minus 2 is 1. And this is where the curvature is concentrated. And the circumcenters of each of these tetrahedra will form the Voronoi cells that we had before. So I have then the structure, I have the edge and codimension 2 edge and the 2-dimensional Voronoi area. And instead of calculating internal angles, I'm calculating deficit angles. I'm calculating dihedral angles. Same formulas in 2 dimension, and the same formula for the sectional curvature in Regge calculus for this block. So this is deficit angle divided by this. Now in Regge calculus, you don't see this. You don't see the Voronoi areas coming in as prevalently. This is what I'm emphasizing in this talk, so you know. You can... And now in 4 dimensions, so for those of you whose mind's eye can see in 4 dimensions, if you work with this long enough, it's not that you understand and can see in 4 dimensions, but you can trick yourself into thinking you can. There'll be the simplex I showed you on the first slide is a 4-dimensional object. The codimension of that is a triangle. So we have a 1, 2, 3, 4, 5 4-dimensional simplices which share a common triangle. And they don't, when you pack them in a Euclidean 4 space, they don't close. There's a little gap again, just like in this model. And that gap, once again, gives you the deficit angle, which is 2 pi minus the hyperdihedral angles, the angles between the 2 tetrahedron faces, which I show here. So here's your hinge, and there's the X tetrahedron, X ABC, the Y tetrahedron, Y ABC. And this edge here, if you expand it, you increase the hyperdihedral angle. If you decrease it, you contract the hyperdihedral angle. So, and the curvature in 4 dimensions of space-time, which I'm going to be discussing for the rest of the lecture here, is again just the deficit angle divided by this dual hinge, this Voronoi area.
Do you need to account for any signs in this context?
You do not.
Yeah.
Yes. Yeah, no. As in discrete exterior calculus, you don't. I've never had an occasion where that caused me any problem at all, even when the circumcenters drifted far away from the simplicial block. So what's fundamental, what's new? What's new is I'm going to tell you that in Regge calculus perhaps we should view things a little bit differently. We should view the fundamental building block in Regge calculus not as a simplex, but as a combination of the codimension 2 hinges and the two-dimensional Voronoi areas, a hybrid block. These hybrid blocks completely tile the space-time, so no problem. And they have this nice factorization, this nice sort of nice duality associated with it, which Anil has dealt with the discrete exterior calculus many times, and with these kite areas and volumes for weighting for various quantities. So this is what I suggest that we view in Regge calculus as a fundamental unit of the simplicial lattice. So the volume of this, now what's beautiful, and this is where Regge calculus starts shining, is that the Voronoi areas are orthogonal to the hinges. So you have 1/2 the base times the altitude, 1/3 times the base, and so forth for volumes times the altitude. These formulas, they factor. So there's a factorization in the dual spaces. That's beautiful. It gives rise to the beauty of Regge calculus. So again, the volume here could be messy. Believe me, the Cayley-Menger determinant with all these edges in it could be an amazingly bad thing to deal with. But you don't have to worry. You just have a factorization here. So it's the hinge area times the dual area, the green times the blue area. And this factor here is your 1/3 the base times the altitude, or generalized to this particular block. It's a generalization of this. And you can build all sort of hybrid elements with edges and 3 volumes, or vertices and 4 volumes, and back and forth between Voronoi and the Delaunay lattice. So I'll emphasize again that the curvature is associated with a codimension 2 hinge. The rotation is the plane. You could pick any plane. It's a conic singularity. So you look at me like the guy's crazy. He can pick barycentric coordinates and have a barycentric area. I know that, but it's not Regge calculus. So in Regge calculus, the rotation plane is this Voronoi area, and it's perpendicular to the hinge. The Voronoi polygram, okay, I said that. So locally, the space-time then is an Einstein space, because no matter how you take the rotational plane in that block encircling the area, the cohomology, I mean the loop encircling the triangle, no matter how you do that and how you orient that, the rotation will always be in the plane of the Voronoi area. So your rotation bivector will be, so it's locally an Einstein space. So in an Einstein space, you can write the scalar curvature in terms of these is d times d minus 1. This is a dimension. The Ricci then would be, in 4 dimensions, it would be 3 times the deficit angle divided by the area. And the Riemann, or sectional curvature associated to that hinge, is the way I want you to think of that, is building the Riemann and getting the components of a Riemann is a more difficult task. And people that in discrete exterior calculus know very well is a difficult problem that we heard about. But within this hybrid cell, it's very simple. So let's see how this works in Regge calculus, because we want to have a derivation of the Regge action in a very simple way with these new hybrid blocks. So you start with a Hilbert action, and you write down this hybrid scalar curvature here. Well, that's just epsilon divided by the Voronoi area times this d times d minus 1. It's very simple. So this is the scalar curvature piece. This is the proper volume, which I showed you on the previous slide. So out goes the Voronoi areas. You don't see those. You don't have to think about those in the action. Okay? But you really should think about those. And the d minus 1 cancels, and you get the wonderful factor of 2, which gives the Regge action. So here's a derivation on these hybrid cells of the Regge action. Okay? Any questions on that? So that looks beautiful to me. Now the Regge equations, you get the same ways. You get the Einstein tensor from the continuum. You vary the action with respect to the metric. And Regge calculus, you vary the action with respect to the edge lengths. And you get 2 terms, the area, variation of the area with the deficit angle, plus the area and the variation of the deficit angle, and that's 0. This term Regge showed was 0. in all cases. And I have mathematicians in the audience, so don't ask me, excuse me, there's a case where it's not true. It's probably the case, but I've learned that lesson. So let me be a physicist for a while. So this variation of the area, it's just a triangle, variation of the triangle area with respect to the edge length, and that's 1/2 L cotangent theta. So this is the Regge equation that you get from the variational principle. And there's no Lagrangian, no matter Lagrangian, so this is vacuum space-time. So this is the Regge equation. So it's a sum over all these hinges that share a given edge L, because I'm varying that L. So no other L's will touch it. So it's just all the hinges, the triangles on an area L, 1/2 L cotangent theta times the deficit angle is 0. And that's the Regge equation. So we can build other curvature tensors. I've done this for the scalar curvature. I've done this for the, well, I have attempted, and I think I have the Ricci tensor, but I won't, although it's published, I wonder sometimes whether I'm missing something. But it works on our numerical examples, which is not a proof. But if I want to move an object to a vertex, then we can write the Hilbert action in terms of an integral, in this case a discrete geometry, a sum over the volumes at a vertex. And so with this tetrahedra here in 3 dimensions, this would be that. This is the Voronoi volume, would be the truncated octahedra, which is also a space-filling block. Okay, so just giving you a, so we can do this in 4 dimensions. There's dual volumes to the vertex. We can write this in the usual Regge form. And then we do the usual trick where we, well, it's not usual trick in a sense, but we look at the piece of this hybrid cell that belongs to this vertex and not the other 2 vertices. So you get this kite area that comes out of it that I passed around. So this is a reduced hybrid block that belongs to this part of this simplex that belongs to this vertex here. So you use this reduced hybrid block and you push these things through and switch the summations here, which works. And you find out that the vertex curvature is just the average over these reduced hybrid areas, these kites, of the deficit angle divided by the average of the dual areas, H star. So sort of beautiful formula here for the scalar curvature. So, everything seems to be tightly held together. So now we have that going on. So now I want to show you what to me is some of the most beautiful thing about Regge calculus, and that's to go beyond the Regge action using these hybrid cells. And let's derive the Regge equation independently, a different way, locally. So once again, this is some edge in a 4-dimensional simplicial geometry. So that's very clear to me, and it occurred to me that when I was first starting this, it wasn't so clear to me in the audience. But 4-dimensional simplicial geometry, and it's built with simplices. You pick one edge out of it. So on that edge, you'll find all the triangles that share edge AB, and there'll be n of them, at least 3. Could be hundreds of them. But you'll find these triangles. Each of the triangle is a repository for the curvature of the simplicial lattice. It's where the curvature lies, as I showed you on the previous slides. Well, also dual to this edge is the Voronoi 3-dimensional cell. It doesn't have to be a cube. It could be one of these blocks here. It could be anything. Okay, so you get this dual Voronoi cell to the edge here, and this is a nice hybrid cell. And there's a 1-to-1 correspondence between the faces of this Voronoi cell and the triangles sharing edge AB. Okay, so each of the Voronoi faces here, you can associate the curvature, integrated curvature over that. That is the curvature integrated over that Voronoi area. So this is the structure that we can start building following Elie Cartan. We can start building the Einstein, the Regge equations. Now, what Cartan was trying to achieve is how it was in Einstein's theory, a deeper understanding of how it is that you could have 2 neutron stars colliding with one another And all that junk that flies all over the place somehow conserves energy momentum. It's coupled to the curvature of space-time, but yet all the matter flows. It flows in that curved space-time, but everything adds up. Bookkeeping is perfect, 0. No creation of source in a 4-dimensional volume. And so how does that work? So you could try to say, okay, well, let's just try to make that happen. Einstein's theory makes it happen because G is equal to T, and you have the contracted Bianchi identity. Del dot G is equal to 0 in the continuum. And that gives you, well, when G is equal to T, you put T in there, and then you have del dot T is equal to 0, and it conserves energy momentum. So you can try to build the Einstein tensor. So you could try with rotations here, and that will give a, that will not give the Regge equation, because what you'll have is, if this is your dual Voronoi cell, then if you go around the faces of that cell with due regard to orientation, you'll pick up a rotation bivector for each face, because you're bringing your gyroscope around the face of that Voronoi cell. When you get back to the starting vertex, the net rotation will have to be 0. It's a topological identity. The one-dimensional edges of the two-dimensional faces of the three-dimensional Voronoi cell is 0. The boundary of a boundary is 0. So if you write that down in equations, then you get the ordinary Bianchi identity, which was in Tullio Regge's paper. And the problem is, and this is the root problem of Regge calculus from a numerical point of view, is that we know that, that infinitesimal rotations commute. Finite rotations do not ordinarily commute. So this box is leaky. So you have errors. So we have, the problem is that if you take the commutator of a product of two deficit angles, 2 rotations, the rotation 1 times the rotation 2 is not the same as rotation 2 followed by rotation 1. You subtract those off, then you get the deficit angle would be 2nd order. The failure to commute will be 4th order. Therefore, the equations are going to be 2nd order accurate equations. You can see this already without doing any numerical calculations. You know what to expect. So this is a problem. So Cartan solved how you guarantee conservation of energy momentum, and hence getting the Regge equation is that you take your edge L, and one of the faces of the Voronoi cell. And I keep putting different faces in, squares, triangles, and just to emphasize that it's not any particular shape. It depends on how many triangles share that edge. And so you have this hybrid cell with the triangle and its dual. And then instead of taking the rotation bivectors and adding them up, what you do is you take with physicists, a torque, or a moment of rotation. You take the soldering form and wedge it into the rotation operator, dp wedge r. And this is the Cartan moment of rotation. So if you do this, then some amazing things happen, because this moment arm here is exactly what we saw before in the variation of the triangle area with edge length, edge AB. You get this vector from the origin to the circumcenter with an opening angle of theta is exactly 1/2 L cotangent theta, which is what we saw with the variational principle. So the moment arm is the thing that comes out of the variational principle. So, and furthermore, because it's a Voronoi duality, it's going to be perpendicular to the edge L. The rotation operator is going to be a bivector, and I said earlier that that bivector lies in the plane of the Voronoi area. So it too is perpendicular to the edge L. So we formed a trivector. Okay? So this trivector here, it has a property that its dual is going to be, there's only one direction left in a 4-dimensional space, and that's along edge AB. So every face of that Voronoi cell is going to contribute to the sum of moments of rotation for that 3-dimensional object, and they're all going to be adding along the edge length L. And what you get from that is you get exactly the moment of rotation summed over all the faces is exactly what you would expect. You're going to get the Einstein tensor, and this is over this hybrid block. Okay, so this is all the hinges sharing an edge L. This is the moment of rotation. And this now is a vector. Okay, so what Cartan shows us, we know that the Einstein tensor is a two-index tensor. It has two indices, mu nu, AB, whatever you want to work in tetrads, David. So what you learn from that is that one of the indices there is this moment of rotation, the dual of the moment of rotation vector, which is L in our case. And the Voronoi volume, its dual, is going to be another edge. And that, in this case, is also along L. So both indices, so the Einstein tensor in Regge calculus is diagonal. It's along the edge L. If you use barycentric volumes, this would not be the case. So this is why this is important to use barycentric lattices. So now our Regge equations are the Einstein tensor, because it's over a volume, so you divide by the volume, and we have a diagonal Einstein tensor. That gives rise to pretty amazing things. You can also take this formalism and add source terms to it, stress energy, and my student Jonathan McDonald former student Jonathan McDonald did this for his dissertation. He did a bunch of different fields. We never tested it numerically, but this is an example of a scalar field on the lattice. And so you can start coupling, because we have the structure here. We know it's just like putting T mu nu in the right-hand side of the Regge equation. So those of you that put neutron stars in your binary black hole codes, it's the same thing here. We could start working and doing things like that. So this is the second most amazing thing. The Einstein tensors are diagonal, and this is the miracle that happens is that, once again, on the any four-dimensional region, Voronoi region, in this case it is a simplex, it has a bunch of three-dimensional faces. Each three-dimensional face will have this hybrid cell and this associated Regge equation. And the Regge equation will be directed along an edge orthogonal to those tetrahedra. So this is the circumcenter of this vertex at the center. This is in the simplicial geometry. This is the vertex of the simplicial geometry. This is the dual Voronoi cell. And there's one edge for every face of this, and don't look at the difference in numbers. I just couldn't get the time to redo the figure. But anyway, so what you get is a flow of energy momentum, because the Einstein tensor is a flow of energy momentum. It is TLL. And it's directed along the edges. So the contracted Bianchi identity in Regge calculus is absolutely trivial. It is a Kirchhoff-like conservation law. So those of you that have contracted Bianchi identities in your finite element codes or your contracted Bianchi identities in the finite difference codes, you may want to think, in the sense of Alexandrov, how you could take advantage of rewriting things in a way that has the flow of energy and momentum locked into the discretization structure. And Regge calculus does that. Is there a numerical advantage to this? I don't know. So I would think there would be. So for each of these, here's one of the edges and here's one of the faces here. So this cancellation occurs again as a topological identity. This is strong. This is what you want in your numerical codes. You want as many topological identities as you can, Gauss-Bonnet, all these other things as you can in your codes. So this is the moment of rotation for this stripe face. And guess what? There's another stripe face. There it is on the back of this tetrahedra. And if with due regard to orientations, these Cartan trivectors, moment of rotations, will cancel in pairs along those faces. And there's no face left unexposed, i.e. the two-dimensional triangles of the three-dimensional faces of this simplex is 0. The boundary of a boundary is 0. And since this is in the Voronoi lattice, it's actually the co-boundary of the co-boundary is 0. This is how this contracted Bianchi identity comes about. So, just emphasizing again, the features that really appeal to me are the fact that these Regge equations are diagonal, it's locally in Einstein space, and that the contracted Bianchi identity is a Kirchhoff-like conservation law, and that the principles of general relativity are applied to the discrete structure, and it's not coming down from the continuum. So I'm going to go over a little bit to give you an idea of numerical applications. So there is an MTW you first read in chapter 21, and Wheeler said that was the place to start an MTW for students. And then when they don't know something, go to Chapter 8 on Riemannian geometry. And if they don't know that, go back to Lorentzian flat space-time in Chapter 2 and work your way through Chapter 21, which is the ADM and initial value formulation. But so there's one Regge equation for each edge in the skeleton geometry. It might seem that there is no freedom whatsoever in the edge links because we have one equation, same as you have in the continuum. But lo and behold, we know that we have a contracted Bianchi identity, and that unlocks the key to the initial value procedure for Regge calculus. It's the key that unlocks understanding the degrees of freedom of the Regge geometry. Because we know at each vertex in that simplicial geometry, there is exactly 4 diffeomorphic degrees of freedom in that geometry. Just as the people in this room paint coordinate lines on Ford fenders, and Wheeler would say that a Ford fender, it's the old days, imagine curve, not funny. A Ford fender is a Ford fender no matter how you paint the coordinate lines on it. The geometry is what's fundamental. One could say in Regge calculus that a Ford fender is a Ford fender no matter how you triangulate it. So there must be a sense of retriangulation. If you have a unique triangulation for that Ford fender, you must be that would be a miracle. That I would, you know, you have then the number of determinable edges is reduced by the number of vertices, 4 times the number of vertices. That's the diffeomorphic degrees of freedom. Number of edge lengths is n1. Number of Regge equations is n1. And then you have the number of contracted Bianchi identities, or constraint equations, or lapse and shift edges. So it all sort of follows and tracks. And this is due, by the way, there's a lot of culprits in here, but Jimmy York came to Texas when I was there, and he taught me the initial value problem. And he said that there's many ways to skin a cat. So do the initial value formulation the way it works with your geometric structure. So I did that. And Bryce DeWitt, every step of the way, would have me, okay, column of things in the continuum, analogous thing in finite differencing, analogous thing in Regge calculus, and fill that out. And he would not let me graduate unless I did that. So that's why all this is coming out. So in Regge calculus back in the 80s, York had led me to thin sandwich initial value formulation because I have, and this is his a hybridization of what he does. He uses densitized lapse, but I'm going to start stepping away slightly. Maybe I'm drifting away slightly from the conformal, but I'll show you what I mean here. So we have constraint equations. You're free to give the base 3 metric on this surface here, but 1 parameter. Call it the conformal scale factor if you want. And up above, you have the 6 metric components, 2 of which are the dynamical degrees of freedom, pi transverse traceless you're used to using, the diffeomorphic degrees of freedom, and the scale factor. And you have your lapse and shift 4 functions here, 3 of these and 1 of these. So you specify all these quantities, lapse and shift, and you have these unspecified quantities. You solve the constraint equations for your initial value problem. This goes over exactly into Regge calculus. So in Regge calculus, we build the 3 geometry out of tetrahedra, and it's in particular these. So isosceles tetrahedra is what I would use. And you can see one of the isosceles tetrahedra here, so you can agree that they pack Euclidean space. And then I distort the edges to model the curvature of the space-time. And those have 7 edges per vertex. This works, by the way, in any lattice, a random triangulation. The counting will also work. And then you have the identical surface up above in the future, 3 geometry. And then you have all these edges, because you have to break this into simplices. So you have these prisms connecting these 2 tetrahedra, and you have diagonal face diagonals, and that splits it up into 4 simplices, 4 four-dimensional simplices. So you have the same thing here. So we have the base geometry is 6. We have 1 conformal scale factor, and I know this because I know the degrees of freedom of the Regge lattice from the contracted Bianchi identity. I have 3 parameters freely specifiable here, pi transverse traceless and a tetrad variable, which I call tetrad, but I don't know whether it is. And then we have the this quantity which you could call the trace of k, the dual of trace of k. And then this is, since we pick lapse and shift, we fix 4 of these edges here, then we can't pick the coordinatization of the surface up above. We have to solve for that. So lo and behold, when you do this, you have 8 equations for 8 unknowns. So it all works out together. Now, it's not as sophisticated as you've seen here, and there's endless discussions on the subtleties here. So I'm flying blind. I'm not instrument-rated pilot, and I'm flying in a very bad fog storm. So this is what my biggest worry is. So this is this is 2 of the tetrahedra, and this is the 4 simplicities that share that. And I have about 5 minutes left, which is not so bad. The evolution is straightforward as well. Once we have the initial value data between this tetrahedral surface, hypersurface, and its one in the future, then we can evolve into the future. There are 3 ways to evolve in Regge calculus. One can discretize the space and have time continuous. That has been done. One can have an implicit where the Regge equations are coupled, and you, like I showed you on the, if you do it naturally, you'll have an implicit set of equations, so you'll have to solve invert a big matrix. Or you can do tent, what do they call it, Doug? The tent pitching, AKA the Sorkin evolution algorithm. So the 2 fields should get together. But Raphael Sorkin came up with this evolution scheme. All 3 we've applied to numeric examples that are non-trivial. All of them give very good results. All of them give second-order convergence. All of them compare with the finite difference codes on simple models. And it looks like, and in some cases, we independently verified apparent horizons and Brill initial data. That was a big rave a little while ago, a long time ago. But we were able to do things that were contributing ever so slightly to the field. So I'm sort of compiled here an examples of things that we have done. Don't have everyone here, but just to give you a flavor, we have evolved and constructed Schwarzschild data, just static, and with boundary conditions and locking conditions. And Wong did this early on. We've done this with our code and 3D. And we've done 3D null-struct calculus in '88, full 3D initial value. Axisymmetric Brill waves, we did in 1999. Binary black holes, Adrian Gentle. Adrian Gentle was a postdoc of mine at Los Alamos and worked with me as a student. He was a student of Leo Bruin. We worked on, with Daniel Holtz and company and Arkady Kafetz. There's so many people to mention that I can't give everyone credit, but we've had Ruth Williams, who's here, contribute quite a bit to these things. More recently, I'm not going to highlight my students, but Shannon Ray has done the Wong and Yau quasi-local energy calculations. He did the isometric embedding of surfaces into Minkowski space using Ricci flow and a pullback method, and the Weyl problem, Weyl solution. And then a discrete Ricci flow, Roy Conboy, which is a Neil Emerho's student who came to me as a postdoc, was absolutely fantastic and helped me correct and put together a better Ricci flow, set of Ricci flow equations. He's at American University teaching. You should hire him. And Shannon Ray is a National Research Council postdoctoral fellow, and he should get hired as well too. Daniel Holtz, he's well off. He's in Chicago, professor. So, Adrian Gentle, so he's a mathematics professor, and but all these people contributed. And here's, Brill wave data evolving and going off the grid. We couldn't run it too long because we had Sommerfeld. We had boundary conditions that reflected. Brill wave and the Misner binary black hole initial data we modeled. And all these are just to show you that we can get, we can pretend like we're serious at this point, but it's going to take a lot of man hours and women hours to get this thing working properly. This is an evolution I wanted to show you so you can see some of the details, and I'll finish in a couple minutes. This is the Kasner cosmology, so you can imagine taking a cube here in a Kasner universe at t=1, and you evolve it, and it will stretch and compress and pancake, stretch in 2 dimensions, pancake in a 3rd dimension as you evolve, and so these Kasner exponents. So you get very elongated blocks, and it's a very simple cosmology. And so we ran this, but in full 3 plus 1D. So this is discrete, the Sorkin evolution, and this is with the tetrahedral meshes. And we looked at convergence here. And this is the volume of these blocks that should grow linearly in time because of the Kasner model. And this is the volume convergence as a function of our scale length. So as we reduce the scale length, we get second order convergence in our solutions. And this is one of the edge lengths that we tracked on here as well too. This is a momentum constraint, which is less than second order convergence with a scale factor. And this is the momentum constraint here. So this is the homogeneity that we looked at because it's fully 3D, so it can evolve and get instabilities and do kinds of things. But it looks like it settles down, but the homogeneity starts getting worse a little bit. This is the dynamics of the edge lengths as a function of time. I think it's 10,000 time steps. And this is the error in the volume. And this is the Hamiltonian constraint and momentum constraint. So they settle down after an initial relaxation period, things you're used to seeing. So just to not, I wanted people to see images, not to get the details, because you can look up the papers and see the great work of Adrian Gentle and Rory Conboy and others. So, so since you apply principles of GR to the lattice, you have, you can start doing things from a geometric point of view, all your choice of lapse and shift. So to me, I want to take my magnifying glass and I want it to look like flat space locally. So Wheeler and I developed a waste function, which is the log of the area of the best simplex divided by the area of the actual simplex that we have in our code. And if you sum those over all the simplices, and you get the elongation measure of the elongation. So we did some nice waste relaxation on icosahedra to distort them and have them go out to uniformity. This is before the curvature flow was a big hit and everything, but we were just playing around. And then you want to have also, as I mentioned, you want it to look like flat space, because locally space is flat. You want it to be puffed out. You want it to look like isosceles tetrahedron. So you're in a region where there's some constant curvature. So you want to, and locally, so you want to keep the curvature times the deficit times the area, integrated curvature. You want to make that small because finite rotations don't commute. So you don't want deficit angles growing. So this is a gauge condition that the curvature times area is approximately deficit is small and controlled. And that competes with this probably, so you have competing effects. But you can already see now that I'm thinking of, you know, minimal distortion will mean something a little different to me than just the equation that York gave us. So the gauge conditions will have a geometric flavor that is real in the lattice that we see, not that the analysis is not. And the minimal shear is another thing that we can, and this is constant mean curvature slices, minimal shear, so we can start building things. That looks awful esoteric to me. But, and this is the most recent application of Regge principles that I've done. It's Ricci flow. David has done this, and others in the room here. But this is an example of the Angenit and Dan Knopf's neck pinching example. We have a 3-sphere, and you pinch it, and everything's symmetric, and then you evolve it, and then it should form a type 1 singularity, and then you can do surgery and excise that, and then they should go into a direct sum of 2 of the prime geometries, in this case 3 spheres. And this is Thurston's geometrization. So we took this pinched dumbbell, and Dan Knopf says, I wish I didn't call it dumbbell in the paper because my name is going to be associated with dumbbell. And and then we evolved it with the Ricci Regge flow equations, and we got to a point where we saw a neck pinch, and then we just cut the neck and the lattice. We essentially cut out that icosahedron, separated them. Then I did this run was not easy because I had to do adaptive mesh and so forth. So my last slide is next. Okay. So and I won't go through the details, but this is the equations that Rory Conboy and I came up for the Ricci tensor at an edge. And then we get decoupled equations, one per edge. And whether more work has to be done on that, it may, and I'm happy to work with anyone on this. I think it's worthwhile in this particular case to work on these. So important points. Regge is suited for complex topologies, and I went over these, so won't spend time. It's, I don't know the relative strengths or weaknesses of Regge calculus compared to what Pablo and other people here do. I just don't know the answer to that. I'd like to know. Principles of general relativity are applied directly to the lattice geometry. And the Voronoi-Delaunay appears to be a very important fundamental feature of Regge calculus, and I hope that's one lesson that comes across in my talk. And the Regge calculus and discrete X they share many singularities, and I think it's equivalent if we do it properly. In a sense, Regge calculus is an application of discrete X calculus too, and I really, your work was inspiring for me, seeing that. Anyway. And then underlying discrete theory appears to be more austere. We get this diagonal Einstein equation, Kirchhoff conservation law. And what I didn't get a chance, I threw that slides out. I threw about 20 slides out, so it's good. But the null-strut equation, if you have null edges in your lattice, which you can put, by the way, it's beautiful because the Cayley-Menger determinant I love to put zeros in big matrices. But all the constraint equations are linear in a new variable, the deficit angle, sum of deficit angles. And there's duality there, so it's beautiful. And with that completes my talk. So thank you. No. It is not. It's implicit in Friedman. In Friedman and Lee's paper, T.D. Lee used it. Williams and Rochek, I believe, used it. Ruth Williams definitely did. They did not put all the pieces together, but it's Shakespeare's quote of George Bernard Shaw, "I am taller than Shakespeare. I stand on his shoulders." So in the Regge community, it was paralleling what was happening in your field for a very long time. I just put the pieces together and understood the contracted Bianchi identity a little bit better, and the Regge equations a little better, and how to put source in it and so forth, and to emphasize the importance of Voronoi cells. But the greats before me saw that very clearly, I think. So, good question. I'm glad you brought that up. Yes, David?
If you evolve in the contracting direction, Kastner is actually unstable to the onset of chaotic mixed-nested behavior. Is that something you might be able to see in the code?
Probably, yes. We could certainly do that. So if it's important to you, I will twist Adrian's arm and he'll fire up his code. I have his code, by the way. If anyone wants, the Regge calculus code in 1+1, 2+1, and 3+1 is freely available. And it's written very well by Adrian Gentle when he was a postdoc with me at Los Alamos. Commented perfectly and written in C. So, yes. But yeah, that's a good point. Yes?
You mentioned that some people have done discrete space continuous time.
Yes.
Could you talk about the advantages and disadvantages in that and actually doing force equal
All right, it's a very good question. And so we did our simulations and Leo Bruin, as well as Adrian Gentle and me, did simulations all the different ways. Flat Friedman, the Friedman-Robertson-Walker, and the Kastner, and so forth. We saw essentially no difference, and that's in a paper in 2012 by Adrian Gentle. So we saw no advantages one way or the other on that. We have done, by the way, for these things, we showed where Snorik does the foundations of this theory. We pick simple models and check that the equations converge to the continuum equations. They do rigorously. And we show that the solutions converge to the continuum the other way, the Cheeger-Muller-Schrader way. So but yes. So I don't, so what David and you were talking about, I should be working on very hard to report to you what's the best way to go, and that's what Doug wanted to hear from me, and he's not. So I don't know the answer to that. But it's very easy to go those three ways: implicit evolution, implicit, and time, and continuous time. That formalism's there.
So, I mean, one of the things that Oscar
Yes.
So are you doing anything analogous to that, or is there sort of a nice way of saying what your gauge is, and maybe, one can figure out why it is well posed?
We used oftentimes zero shift and densitized laps. We did that in null strike calculus. I have used, we have used, so we have used gauges that are nice to use, and we haven't pushed the theory where we should push it. So take this with a grain of salt, the results. It looks good. I made the slide look good, but we have a lot more work to do to push it, and I don't want to be misleading. Oh, that would be wonderful. The Ricci flow we got by looking at form and curvature as well too. I forgot to mention that. That diagram of the edge length came from a mathematician, Foreman, that gave that. So I need to look at this. That's very good. I need that foundation. So good. Yes.
Maybe just one last thing, and just of completeness. Put Schnorr on the spot here, but there's a sequence of papers that where Schnorr tries to recover Regge calculus as a type of finite element method. I was wondering if you could just summarize what exactly you're able to do, rigorously, what we know about the relationship between these things.
Yeah, so perhaps I could say I know less, but with more certainty. Instead of using these boring molecules and the dual two-dimensional surface perpendicular to the Higgs, I interpreted things in terms of measures, so Dirac delta instead. So in that sense, you maybe smear things out on the volume where I have an infinite curve of the
Yes.
and from that point of view, it became important to find out. I wasn't able to prove any convergence from Hannibal speed. That's why I just did convergence of an eigenvalue problem.
So so would it be, so for the 3D Kasner stuff we did, we took the Regge equations and showed that they were consistent, they were in the limit the same as the continuum equations. Is that useful or not? Or just one example though. Yes, Doug.
That result, and most of the results that are known already from this are consistent with
Mm-hmm.
They say that if you take the exact solution, apply the discretization to it, you get something that's close to if you apply the two operators. So if you calculate curvature, so that you get a curvature that is discrete curvature that is in some sense close to the curvature of the one.
Yes.
The first result along those lines is even a little bit greater.
Yes.
More, so then of course there are two other concepts, stability, and if you have both of them, then you get convergence, which means not only is that you solve problems with convergence, there is, as far as I know, no result of stability reversals. More is one result in that direction, which is a three-dimensional Riemann eigenvalue problem, which solves for the eigenvalue of the
Mm-hmm. Mm. I could add a joke to this, is that to me, I applied the principles of GR to the lattice, and the spin foam people tell me that maybe nature works as a discrete model. So I would like to see the theorems that the exact Regge calculus solutions and have a convergent continuum that can agree with it. So, so
Right.